Okay, so here's another problem that is based on essentially what we did earlier. Okay, here there are more angles to deal with because you'll see as we do the problem. So the question is, what is the net force on positive Q? Okay, so whenever you deal with angles, the first thing I'd always like doing is draw your lines connecting the charges. Okay, it gives you a good idea of what's happening. So I would first connect this, or connect this guy. Okay, and then I ask, let's call that the top charge 1, the bottom charge 2. So we can ask, what is the force on charge capital Q due to charge 1? Okay, so let us draw that force, and that should give you an idea. Okay, so the Q's without the signs are all positive, so we know that lowercase q and capital Q are both positive, and so they'll repel each other. As a result, capital Q will experience a force in this direction. So I'm going to call this force F1. In a similar manner, we can figure out the force on capital Q due to minus Q, and since the two charges are opposite in nature, we're going to have an attractive force. It's going to be pulled down. Okay, so we have these two forces. We want to figure out what F1, F2 are, and then we'll combine them using vectors. There are a couple little things that we need to first find. Okay, so it's always a good idea to do this before you've started the problem. You see, in order to find F1 or to find F2, we need the individual lengths, okay, between the charges. So let us figure out the length between Q and capital Q. And again, we know we have a right angle triangle here with sides B and A. So this length is simply going to be equal to square root of A square plus B square. And so is this length, square plus B square. Alright, good. We have the length. We also have to deal with angles. So we have an angle theta here, and by symmetry we know that this other angle also is theta. So once we know theta, we know everything in the problem. Okay, so let's figure out the angle theta. Now here, instead of directly finding theta in terms of A and B, okay, let us find something that we will use in the problems. Okay, by which I mean, once you know F1, you will write the components as F1 cosine and F1 sine theta. So instead of finding theta, let us find what cosine theta is and sine theta is. Okay, so cosine of theta, if you look at this triangle, if this is the angle theta, we know that the angle theta is also out here. Okay, so if you look at that big triangle here, relative to the angle theta, A is the adjacent side and we have the hypotenuse. So cosine theta happens to be equal to A divided by square root of A square plus B square. Okay, and then sine theta happens to be equal to B divided by square root of A square plus B square. So once again, I'm not finding theta directly, because if we were to find theta, then what you would have is that I would do something like this. Tangent of theta would be equal to B over A, and so theta would be equal to tangent inverse of B over A. Okay, and then when I write my components, I would have to do cosine of theta, so I would have to do cosine of tangent inverse of B over A, or sine of tangent inverse of B over A, which is a very messy thing to deal with. These expressions are much easier to deal with. Okay, so now that we have this, let us proceed. Let us figure out our forces. So first, let us calculate the force F1 completely. The magnitude of F1 is equal to K. Now here's the deal. When you have problems that involve all variables, okay, do not try to substitute values for your constants. Just leave them in their letter form, and then we don't have to worry about it. So it will be Ke times Q times capital Q, okay, divided by square root of A square plus B square, the whole square. Okay, so I'm using K, Q1, Q2 over R square. I can simplify this and read out this as KEQ capital Q over A square plus B square. Very good. Okay, now once again, which quadrant is F1 in? Okay, if you look at the picture, let's draw an axis with the charge at the origin, and if you look at that picture, F1 is in the it's in the fourth quadrant. So now we are ready to write F1 in its full vector glory. Okay, and it will be equal to, since the second quadrant, the x will be positive, so it will be KEQQ over A square plus B square cosine of theta, and the y component will be negative KEQQ over A square plus B square times sine of theta. Now we already have theta in our algebraic form, and we know, let's substitute this. So we have KEQQ over A square plus B square times cosine of theta, which is equal to A over square root of A square plus B square, and likewise for sine theta. we replace this with b over square root of a square plus b square. Okay, let's simplify it further. You see the denominators are of the form x times square root of x. And if you know that this is simply equal to x to the power 3/2. Okay, so I will use this idea and write f1 as keq times a divided by a square plus b square to the power 3/2, and then the other one will be keqb over a square plus b square to the power 3/2. Great. We have f1. We're just a couple steps away from writing f2. So we have f1 in its full glory, full component form. Let us write f2 now. Okay. Once again, the magnitude of f2, because of symmetry, is going to be the same as the magnitude of f1. keqq divided by a square plus b square, the square root of this square, and so we end up getting keqq over a square plus b square. Please note that I've ignored the negative sign there because we are going to take only absolute values. Alright, great. Now that we have this, let us do the second bit. Write the components for this one. Now clearly, if you look at f2, it is lying in the third quadrant. That means its x and y are both going to be negative. Okay, so let us use once again our definitions. We negative keqq over a square plus b square cosine theta, and it will be negative keqq over a square plus b square times sine of theta. Once you get this, you can substitute for cosine and sines, and then also use square root x times x equals x to the 3/2, and I'm going to skip a step and rewrite this as keqq over a square plus b square to the power 3/2, and then the other one is going to be negative keqqb over a square plus b square to the power 3/2. Great. Now we have a component in the full vector form. Let us find fnet. Fnet once again is going to be the sum of the two, f1 plus f2, and this gives us the following. If you look at the expressions, okay, f1, the x component of f1 and the and the x component of f2 are identical, except for there is a negative sign. So when I add them up, I get a 0. On the other hand, for the y components, they have the same value and they have the same sign. Okay, so we can combine them and rewrite this as 2 keqqb over a square plus b square to the power 3/2. And so I can, when I combine, so now that I have this, I can write my magnitude directly. I don't even have to do the square root stuff. Okay, and the magnitude ends up being equal to keqqb over a square plus b square to the power 3/2, and it points, okay, due south or along the negative y-axis, whatever it may be. Okay, so the problem involved a lot of stuff. The first thing here, though, before you start the problem, is always to make sure that you get your angles here. Get your angles in terms of the things that are given. Do not do this. Do not do this part here. I mean, you can do it. It wouldn't be incorrect, but then you're going to have cosine of tangent inverse of b over a, and actually, if you were to evaluate it, you should end up getting a over square root of a square plus b square, and similarly for the sine of tangent inverse of b over a should be b over square root of a square plus b square. So you get all those things, find the sides, and once you get that, then the rest is, find the magnitude, find the components, and you end up getting your values. Okay, so hopefully that helps with that kind of a problem.